All right, hope everybody had a good lunch. So I thought I was wrong once, but I was mistaken. So before lunch, we were a little confused about load and store. Apparently everything is running right. I double checked it. ChatGPT lied to me before lunch. So just to be clear on load and store, it's a little bit confusing looking at the code here because you see the store instruction and the load instruction, which are both using X0 as the base register. Looks like they're in different positions. Load has a destination register, store does not. So for the load, this X15 is the destination, this is source 1. For store, this is source 1 and source 2. So these are, X0 is source 1 for both of them. In both cases, that's the base register for the address. So since I was confused about that before break, I just wanted to talk it through and clarify. Okay, did anyone have an epiphany over lunch? Any questions? Okay, so we're going to switch gears now, and so module 3, design team, roles, tools, flows, methodologies. We'll start with a little about silicon fabrication, talk about design teams, what the roles are on the design teams, what each of those roles is responsible for, how they work together. We'll talk about the design tools that are involved in, we've been focused on writing the RTL. We have to get that RTL implemented. What are the tools involved in that? Talk a little about technology trends in the industry and design flows, methodologies, languages, right? We've talked a little about that. And especially you've been introduced to TL Verilog, but just to relate that to other things. So silicon fabrication, here are some wafers. These are from my own personal collection. I brought these around to other workshops, but I didn't care to fly them to Bhubaneswar. And one of them I actually broke on day one of the first first course that I conducted. So I learned a little bit about the actual physical strength of these wafers. Pretty minimal. I'm going to start out by not talking. We have this video from Matt Venn, who is the force behind Tiny Tape Out. This video is Matt Venn doing a lab tour, so I thought it would be nice to use this video so you can get introduced to Matt Venn, who's the person behind the technology that you're working with Tiny Tape Out, and also get a nice tour of a fabrication facility and a little lesson on how chips are made. So I'm going to start that. Just to check with the recording, Ian, do you know if the audio from the computer here is going to carry through? They'll try it and we'll see. Cross your fingers, hopefully we will be able to let this play.
However you're watching this video, inside the device...
Okay, let's... how do we control that?
This will be lots of microchips. Microchips are the most advanced thing that we make, and it takes an enormous amount of people, equipment, and special chemicals from around the world to make it happen. Normally, it's really difficult to get permission to film inside a clean room. But today at IHP in Frankfurt, Germany, I'm going to take you on a special, exciting tour of their clean room. So let's go and see what it takes to turn a blank wafer like this into one full of microchips like this. Hey, Sebastian.
Hey.
Good to meet you finally, face to face.
Welcome at IHP.
Thank you. So you're the person at IHP that knows all about how everything works, right?
Almost everything.
Because there's so many processes involved, right?
That's right. We are about 500 people here at IHP. And in the clean room are working process engineers, operators, and maintenance staff.
So I'm really excited to go and see inside the clean room. What do we need to do to go and take a look?
We need to dress up.
Because the structures on the chips are so small, less than a millionth of a meter, it's easy for a spot of dust or hair to ruin a wafer. That's why we have to get dressed up in special clothing to go inside. And by special clothing, I don't mean clothes for a Met Gala, although I admit doing our work in a Karl Lagerfeld uniform would be pretty sick. Instead, we wear these special clothes. Don't worry, you don't have to iron them, you only have to hold up the sleeves to stop them touching the floor. It's also pretty noisy because they use a lot of fans to keep the air clean, 1,000 times cleaner than an operating theatre in a hospital. As we go up the stairs, air blows in from the left and the right to remove any last specks of dust. Before we enter the clean room, let's take a step back and understand what we're making. I designed this chip to show the time on a TV screen. Inside the chip are hundreds of logic gates joined together into a circuit. Here's one of the simplest gates, an inverter. When the blue input is low, the orange output goes high. It works by using a pair of switches called MOSFETs. They don't have any moving parts, so they can be made incredibly small. At IHP, they make the MOSFETs so small that you can easily fit 10,000 across your fingertip, or 1,000 if you've got very tiny hands. Here's what one looks like from the top and from the side. We build them on top of a disk of silicon called a wafer. These two areas here are called the drain and the source, and this is called the gate. When a voltage is applied to the gate, it allows electrons to flow from the source to the drain. You can see that as the blue voltage increases, more and more orange current is allowed to pass. Building a whole chip involves repeating hundreds of steps, so we'll just follow the process of building this one MOSFET and its connections up to the first metal wires. Okay, enough of the theory. I hope you're still here and didn't close this video to watch TikTok, or worse, YouTube Shorts. Let's enter the clean room at IHP and meet the people and the tools who build billions of these tiny structures 24 hours a day.
Welcome to our IHP clean room. It has a size of 1,500 square meters, and we operate it for 7 days a week for 24 hours a day. And all in all, we have over 100 tools to produce our integrated circuits. The first thing is that they clean the wafer. So they use different chemicals, for example, to clean it from organics, from oxides, from particles. So a batch of wafers containing 24 wafers is immersed in an etch bath.
In the cleaning and wet etching section, they have 14 different tools from 9 manufacturers. These tools can handle whole boxes of wafers at once, or just work on a single wafer. My favourite part of the cleaning process was seeing them spinning around in this silicon tumble dryer. Dryers are used for wafers, but technically they should work to dry any type of underwear. Unfortunately, I couldn't convince any IHP engineers to test this theory, so I had to confirm with the wafers.
After the cleaning, the wafer gets a very thin protective layer out of silicon dioxide, and that's done in a furnace. So the temperature is raised up to 900 degrees C, oxygen is introduced, and this oxygen reacts with the silicon surface and forms a silicon dioxide layer.
Next, we use a process called chemical vapor deposition, or CVD, to build up a layer of polycrystalline silicon on top of the oxide layer. Polycrystalline silicon, or polysilicon for short, is silicon but without the perfect crystal structure of the wafer. In other words, polysilicon is the wafer's unemployed brother, and I will stick to that definition until someone comes to give me a better one. I won't answer that. So far, every process has affected the whole wafer evenly. Now, to start building the MOSFET's gate, we only want to remove the oxide and the polysilicon where there isn't a gate. Photolithography is the fundamental technique that allows us to print millions of MOSFET gates in a single intense flash of light. Because photolithography uses light-sensitive chemicals, the overhead lighting is yellow, giving us that classic semiconductor cleanroom vibe.
We put a light-sensitive resist on top of the wafer, and for that we use a spin coating process. And there the wafer starts to spin and the resist is spread very even across the wafer. We take the wafer together with a mask containing our structures and we load it into the photolithography machine, and they are aligned to each other, and then light is used which travels through the mask and the lens system which projects the mask 4 times smaller onto the wafer.
This is a photolithography mask. This is quartz glass substrate with a thin layer of chrome on the backside, and we also here see a frame with a very thin foil to avoid particles being placed on the chrome, which we would see when exposing, which would lead to imperfections like short circuits or interrupted metal layers. And on this reticle we have 3 different masks we can use for exposure for 3 different layers.
Okay, and which layer is this?
Those two are 2 top metal layers.
Okay.
And
So that's why the structures look so big.
Yeah, exactly. That's why you can see relatively much on this reticle. We also have, there's a lot of chrome here, so you can see structures. We have very bright radicals, like a lot of glass and very little chrome. And we have very dark radicals, like a lot of chrome and very little open spots in the chrome. This is the eyeline stepper. We have an eyeline stepper and a DPV stepper, 365 nanometers exposure wavelength. And this is 248.
Okay.
This uses laser, this uses a mercury lamp. Yeah, this is for like the more buff structures, the bigger ones, like top metal, the last few layers, where we have like 2 micron broad of our metal layers. And this is enough for that exposure. We don't need to use this. Usually you only use the tool that is suitable for the job, but it's the least expensive for what you are doing. Okay. That's kind of like the efficiency part behind it. And so that's why we have an eyeline. We just call it eyeline. It's an SF150 NSR step and repeat system from Nikon. Yeah. And over there we have, as I said, the DPV stepper, step scanning system that we use for our smallest structures, for the critical layers, especially. That's what this tool is for.
So I just saw the wafers rotating.
Right.
Why is that?
The wafers have a notch which corresponds to the wafer crystal orientation to always align the wafer and expose it or kind of process it inside the tool always in the same kind of way.
Wow.
Kind of a simple system like this, just small line, and it kind of just
The machine
tracks it to
finds
the
the
notch.
line, yeah.
Yeah, exactly. Okay.
Which is the most expensive machine in the room?
The one over there, the big one, that's our DPV stepper. Oh, I don't know the exact numbers. I just know it's double digits in the millions.
Yeah, okay.
Yeah.
After the photoresist is exposed to light, it changes its structure, and then we can develop it so we can remove the exposed regions. Once we have the patterns, the photoresist acts as a mask, and we can do the etching then. So to etch our deep trenches, for example.
This is a reactive ion etching tool. So here we are in the maintenance area of the clean room. In these kind of tools, we etch away material, as the name says, and we do this by creating a plasma above the wafer. We have reactive gases above the wafer. They get ionized in a plasma, and the way it's constructed is such that the plasma can react with the material that we want to etch away. And the special thing about plasma etching is that we can actually control the geometry of the structure. Unlike in
Very
steep sidewalls, or actually we can control the sidewall angle. And this is in contrast to wet etching, for example, because in wet etching, when you dip the wafer into the chemical, it etches in all directions, which is called isotropic etching. And of course, if you want to create very small structures, it's not suitable. So that's why we have to use plasma etching.
Right.
Yeah.
That's like the top view. We just saw that robot.
Exactly. So it's a schematic of the tool, and then we can click around on the buttons here, and we see overviews of the individual chambers with all the different process parameters. So you can see there's a lot of gases installed. You have to monitor different temperatures, and everything has to be in a specification.
And this is the one where we just did the
Yes, this
CVT.
is CVD tool, and then we have also additionally 2 etching chambers in this chamber.
Okay.
And yeah,
Okay, so it doesn't just build up; it can also etch away.
we can actually build up something and then immediately put it to the other chamber and etch it away again.
Wow.
So it's like of a combo tool, if you want.
Handing.
Yes.
Just like my 9-year-old nephew's birthday party, the chemical vapor deposition machine contains a lot of different gases. In the machine's case, it needs them. Those gases are all piped up from the infrastructure floor below the cleanroom. This is also where the chemicals are stored, the water is cleaned, and waste products are made safe. It's much noisier down there, and even more packed with equipment. To continue building our MOSFET, we're going to start repeating steps we've already seen. First, we go back to the cleaning to remove the developed photoresist. Then we repeat the photolithography steps to end up with holes in the developed photoresist. We're left with a structure like this, ready for us to visit a new machine in the factory.
In the ion implantation tool, the wafers are loaded and then they are placed on such a big wheel. And then ions are accelerated. It's like a beam. That's what you see here. And the accelerator travels the wafer and then implanted into the wafer. And we use different materials or different ions. We use phosphorus, arsenic, and boron mainly.
And with the machine, you can choose which type of ions and how deep to implant them.
Right, we separate them according to the mass, and with different energies, we can choose the depth of the implantation.
And what is the concentration of the ions into the silicon?
It's really different, depends on the application. Let's say it's from 1 dopant per 100 silicon atoms up to 1 dopant per million silicon atoms.
A really big range then.
It's a really big range, yes.
If you're a fan of particle accelerators like me, first, know that everything is going to be okay. You'll be okay, people love you for who you are. And second, check out the time I used a synchrotron to make a 3D X-ray of my clock chip.
After the ion implantation, the silicon is pretty much damaged, so we need to heal it. And to heal the silicon, we use a process called rapid thermal processing. It's called RTP. And there, the silicon is recrystallized, and also the dopants are electrically activated.
Now that we've finished all the steps to build the active part of the MOSFET, the next part is creating the metal wires that connect up all the MOSFETs into the bigger circuit. To start, we grow a layer of silicon dioxide over everything, which results in a bumpy top surface. We want it smooth, so we're going to grind it extremely flat using chemical mechanical polishing, or CMP.
So we have two sides on it. One side we do oxide,
Removing
removing the oxide, ILD, STI on one side. On the other side of it, we do tungsten.
Okay,
With
removing
tungsten.
tungsten. There's
Yeah.
2 different processes.
Yeah, a little bit. And the recipe is different, and also the slurry we use is different.
Okay.
Yeah, that's the main thing. So I'm just done with the process right now,
Okay.
but I can start the process if you want to see.
Yeah, that would be amazing.
Okay, it's good. I can start it.
Start the process.
The warm-up wafer comes in twice. Then the real wafer we're going to.
Oh, so you have like a dummy wafer.
Exactly.
Okay.
So the dummy wafer comes
Yeah.
first to check the process.
Yeah.
Once the process is fine, once everything is good,
Okay.
you can send the wafer can come.
Okay.
Once the process is not good or something like that, you can abort the process. It's just more like I feel like it's like a safety.
Yeah, I
safety
like
kind
I
of
like
way.
it warm up wafer.
Exactly.
It's cool. Yeah.
Warm-up wafer. That's what we call it.
When I'm looking at the polishing, I'm seeing like this little spark of light. What's
Yes,
that?
that's the optical endpoint. Yeah. When the wafer reaches the limits at which the polish limits or the desired limits, it stops automatically and transfer to the next process.
Okay.
That's basically the goal.
All right. And then this is coming to dress the wheel again to kind of clean it,
Exactly.
clean away the
Exactly. So after using the tungsten CMP, I have to check if there's tungsten rest on it. For this particular process right now, you can see some white cloudy stuff
Yeah.
on it here. So there's tungsten on it. You can see there's little tungsten on it. So I have to see what to do to make sure everything is.
needs to go back in the machine
Yeah, probably.
for longer.
Yeah,
So you're aiming between not enough and too much, and you've
Yeah.
got to get it just perfect.
exactly.
Wow.
Exactly.
Our wafer then returns to photolithography, plasma etching, cleaning, then tungsten vapor deposition for the vertical connections, more polishing, aluminium vapor deposition for the horizontal connections, photolithography, plasma etch, and finally cleaning the developed photoresist. All of this has just taken us up to the first metal layer. IHP's process has 7 metal layers, so to finish the wafer, they'll have to repeat all these back end of line steps another 6 times. You might have noticed that the wafer boxes have different coloured clips. A yellow colour means it's for internal testing. The red colour means it's a hot lot. A lot means a box of 25 wafers, and a hot lot means your box doesn't wait in a queue, it's always jumped to the head of the queue of the next process. That saves time, but it does cost more.
To build a whole wafer, it takes about 600 steps, and that takes 3 to 4 months to produce a whole wafer. Once we build up all the layers, the final step is a passivation out of silicon dioxide and silicon nitride, but there we still have to etch some holes to connect our integrated circuit. After all these process steps and all this waiting, the wafer finally comes out of the cleanroom and is diced into little pieces and ready for use.
After the wafer is diced into individual chips, they're normally encased in a plastic package, making them easier to handle. I mentioned earlier that it's very rare to get a look inside a foundry, and that's because the semiconductor industry doesn't want to share its expensive secrets. As well as IHP letting us look inside their factory, they're also letting us look inside their PDK. That's the library of all the things you need to know to actually design a chip. They're part of a growing movement that's making semiconductors more accessible to everyone. In 2024, IHP plans to let amateurs like you and me get our chips made here. And if you're wondering, well, that's great, Matt, but how do I learn how to design a chip? And will it make me a better person? Then the answer is to check out my Zero to ASIC course, where I've helped hundreds of people like you to design their own chips, and yes, you'll be the best person ever.
Thanks so much for the tour today, Sebastian.
You're welcome. Thanks for coming to IHP.
I hope you enjoyed learning a bit more about how the microelectronics that power our everyday life are manufactured here at IHP. And if you want to learn how to make your own chips and even get them made, then check out my Zero to ASIC course and sign up for the newsletter. Thanks for watching.
Okay, so that's Matt Ben. No, that's Matt Ben. So he's the force behind Tiny Tape Out. And this was a tour of IHP's facility. So this is a fab in Germany, of course. We're using a fab called Skywater, 130 nanometer process. IHP's process is kind of similar. The exciting thing about Sky 130 is that they opened up the PDK, the process development kit that defines the technology so that everybody could work with it. And that enabled, everything that you're doing with Tiny Tape Out, really. IHP followed suit and opened up their PDK as well more recently. So I think there's active work going on, is my guess, enabling Tiny Tape Out to work with IHP's process as well. All right, so let's look at design teams. So various roles on a design team, right? When you're starting off a new project, that project is defined by the business leaders. They work with architects who define the design at a high level. The architects work with the logic designers who are responsible for implementing the RTL, right? So basically, the architect sits between the business leaders, helping to define what the project is, meeting business objectives, and connects that with the lower levels. So the logic designer is the verification team is responsible for verifying the functionality that's created by the logic designers. The implementation team is responsible for implementing the design that comes from the RTL. So they're direct consumers of the RTL. And after the RTL has been sort of signed off by the verification team that it's ready to go, and you want to push the button on the tens or hundreds of millions of dollars that it takes to fabricate the silicon, the design goes off to the fab. When it comes back, the post-silicon engineers are responsible for verifying the physical silicon. So obviously there's a close relationship between the verification engineers doing the pre-silicon verification, the post-silicon engineers doing the post-silicon verification, and all working with the logic designers. So let's look at these roles in a bit more detail. First, we'll look at the chip design process overall. So, essentially following what I just described, but focusing more on the evolution of the project versus the roles. So again, everything starts out with defining the requirements of the project. What is the project? And from the requirements, how are we achieving those objectives? So what's the specification of what we're implementing? What's the architecture that is going to enable us to implement silicon that will meet the requirements? From this specification of what it is we need to build, that feeds the verification plan, right? So how are we going to verify that this design is meeting all of these specifications? These specifications also deliver into the floor plan. So as you start to understand what exactly it is you're building, you can start to floor plan the chip, lay out what logic is going to be where, how much size are these different units going to take, what are the units, what's the routing between the units. This is mostly kind of spreadsheet work to make sure that the the architectural plan is implementable. You'll also have some early modeling for estimating the power to make sure you're meeting your power budget, and doing architectural models and performance models to make sure that, well, for one, at a high level, your architecture is functioning correctly, and also that it's performing to specifications. And of course, all of this work, you know, it's not just a forward flow through all of these steps. These steps are all learning experiences that feed back into the previous steps. So your performance model might tell you there's a performance issue, and that would feed back into the architectural spec. You might have difficult, you know, floor plan issues that require rethought. And even the requirements are not static. The ecosystem changes around us, requirements change from above. So, you know, you're sort of starting out at a high level and working your way down to more detail. So more detail means floor plan becomes implementation, where you know, once you actually have RTL to model your hardware, you can actually run logic synthesis and place and route tools to understand your implementation in more detail. Also, as your RTL model is coming together, of course, also driven by the architectural spec, you work on your verification environment and connect that to the RTL to verify the functionality. All of this is the modeling that's done. You're also working with those models. So the performance and architectural models allow you to do performance modeling and verification work. The verification environment and the RTL enable you to do functional verification work. So writing test cases and running those test cases and debugging those failures, etc. So again, once essentially once you've checked off all of the items that you defined in the verification plan, and the verification team says, okay, we believe this is, you know, 99.9% likely to succeed, or whatever your sort of confidence targets are, you go ahead and tape out the chip, which means you provide the data that goes off to fabrication and becomes the silicon, and the silicon comes back, and you start the post-silicon work. Any broad questions? So just diving into each of these roles in a little bit more detail. One slide on each, well, one slide on most, and then we'll go more into verification. So the architect is defining the project. They're balancing the business needs with the feasibility of implementing this thing. Mostly they're working with slides, you know, high-level block diagrams, spreadsheets, this kind of thing. Not so much the tangible, simulatable models, although they might be working with some high-level models, performance models as well. Generally not hands-on with the RTL. The logic designer, basically, logic designer's role is simple. That's what you were in this course. Logic designer has one responsibility, and that's delivering RTL. But to do that, you're balancing, you know, all the trade-offs. You're balancing trade-offs for area, performance, power. People talked about this term PPA. It's power, performance, area. Those generally are the three main characteristics of the silicon that you tend to be focused on optimizing. Certainly not the only ones. So, you know, focused at the RTL at the logic level. Verification world is a bit more complex than the RTL world. Verification tends to deal with a myriad of languages, myriad different tools, environments, ways of approaching a problem. So in general terms, the verification engineer is creating the test bench. That's sort of everything surrounding the RTL. That includes transactors that are driving stimulus into the RTL. So the tests define what that stimulus needs to be in some way, right? For the CPUs that you guys designed, that would be a test program. The transactor is responsible for applying that test program to the model. So in the case of the CPU, that's pretty simple. That's basically an assembler. You get the code into the model, into the instruction memory. For most designs, there's a little bit more intelligence around taking that stimulus in some, higher level description and actually driving the physical pins of the design under test, the DUT, which would be your RTL model. And this happens at all levels, right? You have an environment like this at the unit level. Maybe your unit is your CPU core. You have an environment like this at the full chip, which might be a many core chip, and maybe you've got, like Apple's designs, the M series, M1, M2, etc. They have CPU compute engines, they have AI accelerators, they have GPUs all on the same chip, right? So you'd have a verification environment at that level as well. On the other side of the RTL model, you are checking the outputs to make sure they're correct. So you need to monitor the outputs. The monitor, is basically like in the opposite direction. It's taking the pin level details and up leveling that in some fashion. Other tools connect, at the interpretation of the output signals. So models and checkers, coverage monitors looking at, generally looking at the internals as well of the design under test and making sure that the stimulus that you're providing is covering the situations that you intend to cover. You might have some visualization, you might have performance modeling that's kind of watching over the RTL to make sure that the RTL and the performance models, performance characteristics are in line with each other. And in addition to all this, so this would be dynamic verification or functional verification that's based on simulation. We also have formal verification, which is a more mathematical, proof-oriented verification to prove properties about the design. Prove them 100%, for all scenarios, not just for particular simulations with particular stimulus. The verification engineer is also perhaps responsible for completely, well, not completely, but a partially separate world that looks very similar, but is based on hardware emulation instead of simulation. So hardware emulation is using, generally this is FPGA-based platforms for modeling the behavior of the hardware. Basically, you're running your design in the FPGA instead of running it in simulation. So the RTL DUT, design under test, is synthesizable and therefore can be run on the FPGA hardware. The rest of these components may or may not be synthesizable, and if they're not synthesizable, they need to be run in software on a host platform. So these hardware emulators will have FPGAs for running the design under test. That'll be connected up with a host system that would run the transactors and monitors, etc. Obviously, the FPGA is executing behavior very quickly. Whatever you have running in software is going to run, by comparison, much slower. So the speed of these systems tends to be gated by the software components. So often these components need to be different for the hardware emulation platform than they do for simulation. There's a large push right now to make those two environments more compatible with each other. TL Verilog actually potentially plays a very important role, since TL Verilog is modeling things at a more abstract level. The modeling methodology of TL Verilog is more appropriate for performance modeling than RTL would be. If you model these components, the transactor and the monitor, using transaction level Verilog, you're naturally synthesizable. So you can fit these components then on the FPGA as well, and thereby not limit the performance that you can get for hardware emulation. But especially since the simulation-based environments generally come together sooner. The hardware emulation often, although it shouldn't be, often is an afterthought. Often these components get developed in a way that's not friendly to emulation. So there may be some additional work to develop transactors that are appropriate in this environment. You know, you can afford to do a lot more with the transactors and the monitor in simulation, since your simulation speed is limited by the simulation of the RTL anyway. When you're doing hardware emulation, you're really trying to hit those deep simulation cases. So it might take days of simulation to get through just hardware reset alone on a full chip system. So you might use the hardware emulation platform to do the reset sequence. You might use it to do Linux boot, for example. And you can't afford to have the same level of software running in that ecosystem as you can pre-silicon when your simulation runs are shorter. Not pre-silicon, in simulation. So there might be considerable work to rework the nature of the transactors and the monitors. There'll be things that you would run when you're running simulation that you would disable for hardware emulation. Essentially, though, the nature of the modeling kind of fits this picture either way. And so the physical designer, and we're going to come back more to the verification role since it is so intricate. But the physical designer is fed the RTL. They run logic synthesis, place and route. Right? So logic synthesis is coming up with kind of the gate level model, and then place and route is placing the gates physically on the across the silicon area that's available and connecting up the gates. So the physical designer will be responsible for floor planning the different units, and then implementing, running the logic synthesis, place and route on these different units, getting the connectivity all correct, and coming up with the implementation of the design. And again, this is all iterative, right? So the logic designer is working on the RTL, the implementation team is running logic synthesis, place and route, they uncover timing issues, they uncover floor planning issues, they feed that information back to the RTL designer, and it's a lot of back and forth. After you tape this thing out, silicon comes back. Post-silicon engineer is responsible for verifying the silicon. So primarily, so post-silicon, we have platforms called testers. The testers, you drop the chip into the tester, you hook up all the ins and outs. The tester is going to drive what are called test vectors, which is just all the 1-0 patterns at the inputs, and check the 1s and 0s coming out at the outputs. Very simple in concept. Post-silicon, you're also going to test for reliability concerns, putting this chip under harsh conditions. You'll send it over to Los Alamos Labs, which is high elevation and tends to get a lot of radiation and activity, particle strikes coming from the atmosphere that can cause mischief on the physical silicon. And simulated harsh conditions in labs. They'll also test the power characteristics of the model. One of my brief roles was coming up with the power virus for one of the chips that we created. So the power virus is the test that will be run to stress the power as much as possible on the chip. So every chip that comes out of the factory is going to go through a standard litany of testing. The power virus is part of that. So they're also kind of in line with that, responsible for yield testing and binning. So one design, one chip is not necessarily one product, right? So for example, I worked on x86 CPUs, so maybe we have a generation of x86 CPU that's a 16-core design. We'll sell that as a 16-core high-end design. We'll also sell that as a 12-core design. And if we get a piece of silicon and we run that through manufacturing tests and we find that there's a bad core or two on it, we'll drop that into the 12-core bin and sell it at a cheaper price. And also the clock speed of the chips, right? So we'll crank up the clock on these parts and see where they fail and then back off a bit and bin it appropriately into a particular clock speed bin, right? So over the years, over the course of my career, the binning strategy has gone from no strategy, it's one chip, it's one product, to incredibly complex binning strategy that involves multiple people to sort the whole strategy out alone, and then, you know, more engineers to execute on that strategy post-silicon. Let's see. Of course, you know, their primary role is to, you know, early on, you get the first silicon back. There are obviously going to be a lot of issues with that silicon. They're trying to bring it up. They're trying to get out of reset, get through the boot sequence, get through Linux boot, and get the parts stable so that we have some stable parts to do more tests on. And they're working with the pre-silicon team to debug issues that they find post-silicon, to, once they find issues post-silicon, to somehow recreate that in the pre-silicon world. And of course, the post-silicon engineer's job doesn't just start when the physical silicon comes back. There's a lot of preparation work to work with the pre-silicon team to make sure that all of the functionality that's going to be important for the post-silicon team to do their jobs actually gets into the silicon so that they have the visibility, right? I mean, it's a very fundamentally hard thing to debug a piece of silicon. It's a black box. It's very hard to see what's happening inside. You know, you've debugged in MakerChip where you have access to all the signal values. You can figure out what's going wrong. You've also worked with the design on the FPGA, right? Once it's on the FPGA and it's not behaving right, the bug that we had with the debalancing logic, for example, I mean, we're working with a very simple design, yet we had a bug that was difficult to debug. Very difficult when all you have is a black box that's, you're telling to add 1 and it's adding 6. What's wrong? How do you see that? You need to put hooks in the hardware so that you can inspect what's going on internally and figure these things out. That can be quite intricate and challenging, especially since you don't know what's wrong until it happens, and if you don't have the visibility at that point, you're kind of stuck, right? That's been a multi-million-dollar process wasted if you can't figure out what's wrong with the hardware. So, you know, as I said, all these different roles, the engineers are all working together. It's a highly collaborative process. At least it should be. If it's not, you'll never get silicon out the door. So how are these groups working together? You know, we have the lines between them kind of indicating where there's a strong connection. The logic, since the RTL is kind of the center of the universe defining the behavior of the silicon, tends to be a very central role communicating with pretty much everybody else. But so the logic designer is working with the architect to define the design that's being implemented, right? The architect is providing the PowerPoint level. The RTL engineer is implementing that in code. Logic designer is working very closely with the verification engineers to verify the functionality that they're working on, right? Defining the verification strategy and debugging failures when they pop up. Working very closely with the physical designer, right? When there are physical difficulties with the design that require rework at the register transfer level, that feeds back to the logic designer. And then when we actually do have silicon, right, the verification and logic designers especially are very involved in the process. I mean, many of the folks who are pre-silicon verification engineers and logic designers will then pick up responsibility post-silicon as well. And they're all working closely together to understand the failures that happen in production, take those failures, reproduce them in the pre-silicon environment so that they can be debugged And as I said, the pre-silicon, the post-silicon engineer is doing a lot of preparation, working with the logic designers to feed in these features, which would be referred to as design for debug and test, especially to make sure those features are in the RTL model. So verification engineers and post-silicon engineers are also working together closely on the environments to make sure they have a post-silicon environment in place for verifying the physical silicon and leveraging as much as possible from the pre-silicon work. So, you know, test content that's written pre-silicon, we want that to be portable so that you can run that post-silicon as well. And that's especially where there's a lot of activity right now with a methodology, a tool, a language, I don't know, to support this called portable stimulus to write tests in a way that is portable to post-silicon. And of course, in addition to those roles, you've got managers, you've got folks that are focused on things like performance modeling and power modeling. You've got a team of folks probably focused on reliability and scalability, so making sure that the designs that are fabricated are as resilient as possible and scalable to large systems. You've got analog components on the chip as well, of course, and you've got a team responsible for the tools and methodologies that are used by the organization, so the internal EDA. So this slide is kind of illustrating that design is all about trade-offs. It's really more art than science. You're balancing a lot of conflicting needs and trying to come up with silicon that best balances all those needs. The boldest item here is schedule. That's always a strong message early, and it's an even stronger message late as the schedule starts to slip more and more. So, you know, getting out the door, I mean, a lot of the benefit that we get from next generation silicon comes from the technology benefit, the scaling of the technology. So just getting something out the door on the new technology, you're getting a performance boost. So you want to get to that as quickly as possible. You get additional performance boost and functionality improvements, et cetera, from architectural change. But a lot of the benefit is just from getting the old design to work on a new technology and getting that out the door as quickly as you can. So schedule is always number one. I mean, I think every project I've been on, by the end of the project, we have a meeting and our leader stands up and says, top 3 priorities are schedule, schedule, and schedule. And, you know, all these other things as well, right? Performance, power performance and area, PPA, right? Those are big. You want to balance, find the right balance in those. And of course, you have different customers for your project, for the silicon, and you want to satisfy the needs of all those customers, which of course are not all the same, right? So obviously correctness is important, and it needs to work. So scalability was kind of making sure that you're covering a range of customers, from the small scale designs to the customers that are going to, you know, build massive systems out of the chips. Serviceability, performance, of course, risk, scope, right? So as much functionality as possible to cover as many customers as possible, but then the more functionality you add, that takes away from other aspects of the design which affect your other customers. So again, it's all about balance. Reusability. This always, I don't know, was a point of contention for me. I always thought it was important to make sure that all the work, engineering work that we do for one project carries over to the next project and we can benefit from it. Organizationally, we tend to be designed for the project and all of our goals are about that project. But okay, any questions or thoughts? Yeah, so this slide is more of me rambling. I don't know, I probably shouldn't have put this in here, but I've got the stage, so I'll ramble about my hot issues. So I always felt that the design team should work in a bit more of a robust fashion, right? It tends to be the largest voices on the teams are the ones whose whatever their hot button item happens to be, we tend to, you know, kind of skew things toward the loud voices. So to me, it's kind of a simple framework here. The architects are defining very big picture, what's the project, right? There's some curve that's balancing all these myriad factors. The architect is putting us generally here on the curve, right? This is what we want to target. And then the logic designers are making these microscopic decisions day to day that move the dot small amounts, right? So at this scale where the logic designer is working, we're in a linear region. So to me, the role of the architect is to define where we are on the curve and define the linear trade-offs in this whole complex trade-off space, right? And once you have that linear equation that the architect could define, right, you can put it all in terms of dollars if you want to, right? What's the value of performance for this product? You've got some linear factor for the value of a delta performance or a delta power or a delta area. And you can put that all in a big linear equation. Once you have that equation, now you've got the framework to make the day-to-day decisions about, okay, if I make the cache twice as big, is it worthwhile or not, right? Let me find the sweet spot for the cache size. So it, you know, in my mind would take away a lot of the meetings and a lot of the back and forth. Verification, so essentially the whole design process is a process of going from some very high level definition of what you're building to refining that down. So you go from, in our case with the CPU, an instruction set architecture that you need to implement, down to the register transfer level that's implementing that functionality. Maybe there's a model or two in between there as well. From there, it's tools doing the work to get, primarily tools, to get to schematic, and from there to layout. Each of these steps is, you know, in this case, to get down to the RTL, it's a manual step. Lower than that, it's tools. Regardless, something needs to be in place to verify the process, whether that process is tools or humans. Humans wrote the tools, right? The tools can be faulty. So functional verification and formal verification is all there to test this work. Since that's human work, that represents a lot of human effort to verify. Logic synthesis, we have, you can do formal verification or gate level simulation to verify that the schematic level, gate level design matches the register transfer level. Place and route, we have something called LVS, layout versus schematic, to verify. So this is basically two independent tools, you know, to cross-check each other. One doing the work, one making sure the work was correct. So I'll go in more on verification, since verification is a very important role that represents a lot of the work in the design process, and also we didn't focus on verification in the work that you did in the course. There's a document called the International, is that right? Yes, International Technology Roadmap for Semiconductors, ITRS. You know, it was a very broad effort to define where semiconductors are headed, identify crucial issues, help guide government decisions, things like that around the industry. So this document, I don't remember what year this was. This was, you know, several years back, but identified verification as a crisis area, and of course it's only become more of a crisis since. Verification is hard, right? Like I said, logic design is just RTL. So you're right, and below the RTL we have tools that help us verify that the work that we're doing is correct. But verifying the RTL requires many tools, many methodologies, and it's really difficult to know when you're actually done the work. One bug can result in a need to respin silicon, easily hundreds of thousands. That's a low ball, I think. And months of work, which could mean going out of business, right? It's a big deal. Bugs matter. Generally, today we see about 2-to-1 for verification engineers versus logic designers. The amount of code that verification engineers produce is probably 4-to-1 versus logic designers, right? Which kind of makes sense. Verification creates as much, as much as they can to provide stimulus to this model, whereas the RTL, you really want it to be carefully maintained and controlled, and you don't want, churn in the RTL is problematic. For verification, it's throwing as much as this thing as possible. In a sense, I mean, you want to do that in a thorough way where you can measure progress and so on. And after saying all this, there are very few colleges that offer courses in verification. I'm going to assume there's not a full course on verification at IIT Bhubaneswar, and that's certainly not unusual. The unusual is to have a course like that. Some of my colleagues that I've worked with for many years are actively driving verification curricula into universities. So the nature of bugs, right? Early on in the design cycle, the designs are not very mature, they're evolving. Bugs are easy to find, so you have a lot of bugs. They're not worth very much. As the design matures, there are fewer bugs out there. The bugs are harder to find. They're more complex in nature. They're also incredibly more costly, right? I mean, when you have a piece of silicon in a customer's hand and you stumble over the Intel floating point bug, that costs you big time. So it's just this kind of progression, somewhat exponential in nature, of the number of bugs versus the cost of the bugs. The more disciplined you are about verification, the more this bug curve looks like this bug curve, right? Where if you're focused early on robustness of your verification infrastructure, you're not spending as much time just trying to grab low-hanging fruit and identify bugs quickly. You're not going to catch the easy bugs so fast, but you're going to build a more robust environment, and over time you're going to start more reliably finding the bugs and have a more regular sort of tail. The solid line here is, that's more reality. This is more aspirational. A couple plots I pulled from Wilson Research Group, which does studies and surveys and so on in the industry. So I don't know exactly this kind of the range of ASICs that were covered here, but this is the data they collected over, I guess there's a 2-year cadence here on the data, so this is over the past 6 years or so. So percentage of projects that are successful on per silicon, and you see, a number of projects take 7 spins or more before the company goes under, I guess. These are the companies that were left around to talk about it in the Wilson report. This breaks down the nature of the bugs that cause respins to be necessary, right? So this is the far right tail of the bug plot. One of the interesting things to note here is that logical or functional bugs, well, first of all, if you look at all these bars, you'll note that they add to more than 100%. I believe what we're looking at here, I believe the bars will total the average number of respins, right, as a percentage. So if we're looking at an average number of respins of 2.1 out of this data, whatever it might be, the total here should be 210% on these bars. So logical or functional bugs is around 50%, right? I don't know what that is as a percentage of the total, but it's a fraction of the total. The rest of these, almost all of the rest of these, are analog in nature, physical in nature. So the point being that digital logic, functional bugs, is easier to verify pre-silicon than these physical and analog type of issues. I think there are 2 bars here maybe that are digital logic in nature, safety features, security features, and I think the rest are kind of analog-y. So clocking, tuning of analog circuits, crosstalk, so wires interfering with each other, signaling interfering. Power consumption issues, mixed signal interfaces, yield or reliability issues, so timing paths not meeting timing, firmware, software verification in all of this can be a significant effort on its own. I'm not really talking much about the software and co-simulation, co-verification of your software or firmware together with your hardware, but that's also a big topic. Yeah, so we've got timing paths that are too slow and timing paths that are too fast. Both can be problematic. IR drops, again, physical, very physical in nature. Safety and security, you'll notice just sort of popped up on the radar for the last survey. Safety and security are becoming increasingly important. Governments across the globe are very focused on security. So any thoughts or observations about the data? Bugs happen all the time. It's a reality. So just some data on Intel 8th generation, 9th generation, 137 errata, since fabrication of the silicon. So mostly these are things that, there's some sort of workaround for in software, or they only relate to certain customers, and we're still able to produce the silicon and ship it off. But yeah, just to make the point that silicon does not come out perfect. A look at verification languages. So you can use VHDL or Verilog for your verification environment. I don't know why Verilog is so much bigger than, System Verilog is bigger. System Verilog, the delta of System Verilog from Verilog is mostly around verification functionality, features that, UVM you may have heard of is a library built on the System Verilog features for doing verification. Vera is a language that, you can see didn't get huge traction for doing verification. Many of my former colleagues, some of my former colleagues were off in that world a bit. System C is C-based modeling of high-level behavior, and you can use that for verification. SpecMan E also, some of my former colleagues worked on SpecMan E, another language for doing verification. C++, actually Vera, I'm trying to remember now if that was incorporated into Verilog in some form, but I forget the details. C and C++, when I started my career, most verification modeling was done in C++. And then System Verilog came along and took the lion's share of that. And these other ones, SpecMan E, Vera popped up, and then kind of never took off in full. PSS is the portable stimulus standard that I was mentioning. And I think the most interesting one here is this bar, which is Python. So what is it, CocoaTB, I guess. Open source, right? All the rest of these are commercially driven. this is the impact open source is having, right? It was 0 in the last 2 surveys, and now it's a substantial bar, right? So the trend line here is pretty astronomical. Hard to project from one data point, but I think it's telling. So a closer look at pre-silicon verification, right? We're starting off with the functional specs. We write a bunch of verification test plans. As I said, you're going to have unit level models, many of them. You're going to have a full chip model, a system level model. You're going to have a model for emulation. You might have models in between the unit level and the full chip level. So all of these are going to have verification plans. So these are the models. This is the work. You're going to be using the verification plans to, count through all of the items in the plan and make sure you've got tests that achieve the desired coverage goals. So the test plans are going to incorporate, a specification of what all the coverage is that each category of testing is trying to hit. And then the coverage monitors are making sure that you hit those cases. And that's giving you a level of confidence that you're, kind of exercising the logic, all the corners of the logic as best you can. Yeah, of course, there's the actual debug work, right? So you create these models in order to do debug. You're debugging not just the DUT, but also the environments themselves to stabilize all the modeling so that you can run all the testing. Once all of your test plans are complete, and you feel you have adequate coverage, and everything is signed off on all levels, you'll tape out the design. So drilling more into the nature of especially the checking environments. So this drawing illustrates what would be known as a shadow model. So this is kind of the most simplistic view of creating modeling and checking for a design under test. So the shadow model would be a model that's pin accurate with the inputs and the outputs. So you drive your stimulus to your RTL, you drive your stimulus to your shadow model, you check the outputs of the shadow model versus the RTL and make sure they match. Okay. What tends to happen when you take this approach is that the gory details of the RTL tend to get exposed to the extent that the shadow model has to pretty closely match what the RTL is doing. You really get value when you can abstract things. So shadow model tends to force you into kind of a low level of verification. So what you can do to improve that is build models. So first of all, you stick a monitor on the RTL that's up-leveling the interpretation of the pins a little bit. So you're not specifically checking, maybe, well, I don't know, CPUs are not a great example here, but anyway, you're not specifically checking pin accuracy, but your monitor is interpreting those pins at a higher level of abstraction so that your reference model doesn't have to be, sort of incorporate that. By breaking off that function as a separate thing, you can share that work of abstracting the behavior for other models that are overseeing the behavior. Your reference model then doesn't have to know the individual pin level, and also your monitor can tell your checker, okay, this is what the RTL did. Your checker can tell the reference model, and that might impact the modeling, right? So for example, in your CPU, what's a good example? So we didn't do a branch predictor, but if we did do a branch predictor, it would be predicting take it or not take it. It doesn't matter functionally. It shouldn't matter whether it was taken or not. The CPU should function correctly. It's a performance feature. So it should be fine for either choice from a functional correctness perspective, but maybe the reference model has an easier time doing its job if it knows the choice that the RTL made. So as long as you're careful about it, it's okay to feedback that sort of information from the RTL to update your reference model and simplify things potentially. So you might have a little bit of connection in this direction as well. So yeah, so basically by up-leveling things, so for example, also you don't care from a functional correctness perspective when you're retiring instructions, you just care that they retire, right? So when the CPU retires an instruction, you'll check that it was correct. A shadow model would have to model the cycle level behavior and know when is the instruction going to retire, what's the exact cycle. In this picture, the reference model doesn't have to be cycle accurate, it just has to know this is the instruction that ought to retire next, and when it does, this is how it should be characterized. And the monitor can say, hey, we retired an instruction, and at that time you check it. Right. And this, I guess this is what I was saying earlier, is it's sometimes okay to look at the internals, right? So this would be representing that you're looking inside to see, was the branch predicted taken or not? And you might use that to update the way you model the behavior in the reference model. You have to be careful about this, of course. You should only be looking at internals for decisions that don't affect the functionality of the design, such as a branch predictor. Just to show kind of a common technique with these reference models, we'll stay in the context of a CPU, right? This RTL DUT might be, let's say, the guts of the CPU core, not including the instruction memory, so it's seeing instructions coming from the instruction memory. The reference model would look over those instructions and say, okay, I got this instruction, let's remember it. It's going to come out sometime later. When it comes out, we'll check everything off. So it's very common to use what would be referred to as a scoreboard to hold on to that in the case of a CPU instruction. So it's basically the scoreboard is watching things go in and then checking them when they come out. So you store away everything that came in, all the characterization of what that thing was, and then when you see it pop out, you check it off, remove it from the scoreboard. Assertions are, very low-level checks that might be internal in your design, right? A lot of our verification is focused on treating something, for the most part, as a black box. So you don't care how it's getting done, what's happening internally. You just want to make sure that the behavior that you're seeing from the outside is right. Assertions, they can be internal. You sprinkle them everywhere. Assertions are not your level of completeness for verification. Assertions are identifying bugs closest to the source as possible. They're capturing design intent. So, we've looked at muxes a lot, right? If you have a mux where the selects should be mutually exclusive, you might write an assertion that says, these signals that are controlling the mux select should be mutually exclusive. Mutually exclusive meaning at most one of them should assert in any given cycle. So assertions might also have a time aspect to them, right? For every request that we see, there should be a corresponding response within X number of cycles, right? Is maybe an example of a temporal assertion. Mostly the assertions, at least ideally, are written by the designers, capturing the design intent. So as you're writing your RTL model, this is what you have in mind. If there's a property that you can express as an assertion, that helps. You'd be surprised how many situations like this, you sort of think, okay, well, these are mutually exclusive. That's guaranteed by the logic, but something's going to happen somewhere along the way that breaks that. And if your error message is these signals are mutually exclusive versus the value in this register is wrong, right? It's a lot easier to debug. Just looking at an example at a code level. So this is system Verilog assertions, this SVA. So this originated as its own language and then was incorporated into the system Verilog standard. That's kind of the nature of the system Verilog standard. It's pretty much a vacuum for and an approval process. Kind of all these different technologies that have evolved from different places have gone through IEEE for ratification and been incorporated into System Verilog. So when you're defining an assertion, you first define a property. So here we've got a property that says signal ready has gone high within 5 clocks after a start was asserted. I'm not going to explain the syntax here, but that's what this says. Once you have the property, then you apply that property as an assertion. You assert that that property holds. So if the property does not hold, report an error. Anybody wondering why verification engineers exist? Why can't the logic designers just get it right? Why don't the logic designers verify their own designs? We don't write software and expect somebody else to verify our software, usually, although large teams will do that. You know, you do have QA teams and whatnot. But it's much more the expectation in the hardware world that the verification work is done separately. So there's a couple reasons for this. One of the main ones is the second set of eyes, right? Everyone has biases. Everyone overlooks things. I do it all the time. If you have somebody completely independent from you looking over your shoulder, their biases are different. They're likely to, you know, catch things that you might miss. Also, the nature of the work is very different, right? A logic designer tends to be focused on the common case, right? The logic designer cares about performance. They care about their implementation team as well as the functional correctness, right? Functional correctness is one of the many things in this earlier picture. And it's not even a huge, you know, it's a big one, but it's not a huge one. Logic designers worried about all these things. The verification engineer is concerned about correctness. Full stop, I guess. So, you know, it's good to have a team of engineers with that specific focus since it is important. Yeah, so it's a form of specialization and division of work, right? Do work in parallel, you specialize. The skill set required in verification is very different from the skill set required in logic design. Logic designer is responsible for RTL, thinking about hardware. Verification engineer is very savvy about software worlds, ecosystems, languages. You know, it's just a very different discipline. So yeah, this last, very likely the logic designer is bringing up their design to a certain level of stability, but then the remainder of the work is picked up by the verification engineers. So the verification engineers are focused on not just the act of verifying, but creating the whole environment that enables that. Let's drill a little bit into tests. So the transactor, of course, is driving the tests into the DUT. The tests, we have, you know, different types of tests that would drive that DUT. So we have a focus test. In the case of a CPU, would be a program, right? It's doing one specific thing, trying to exercise very specific scenarios. We have random testing and varying levels of randomness in the testing, right? So the random testing, of course, is trying to give us a smattering of activity in the chip. where the focus tests may be drilling down into a very specific gnarly corner and trying to exercise something that if you just throw random stimulus at a design, you're unlikely to hit. Also, the focus tests tend to be easier to write, so you might do a lot of that early on for the path clearing kind of activities to make sure things are generally healthy enough to apply the random stimulus to, right? Focus testing, when something goes wrong, it's easier to understand what went wrong because the test is focused. You kind of know what it's trying to do, whereas the random test, you have to figure out what it actually did to a greater degree. We also have regression testing, right? And this is our way of making sure we don't go backwards. So as much as possible, as you're developing tests, you try to enable those tests as regression tests, meaning every time you make a change to the model, the regression tests will be run against that change and make sure they're still passing. So it's our way of making sure that we don't step backward. Anything that's in the regression test, that's a gating function for changes getting into the model, so they prevent bugs from getting into the design. Obviously, you want to balance the sort of the magnitude of regression tests versus the quality of the tests. You don't want regression to take 3 days to run. That's going to slow down progress on getting changes in, but you also want them to get good enough coverage that you don't have bugs creeping into your design that was once stable. Functional coverage. So we want to make sure, and I think we break at 4:15, right, Srinivas? 4 o'clock is our break. So functional coverage. So this is the kind of thing that would go into the test plan, right? So this is a coverage matrix showing that we want to make sure we're hitting various scenarios in the design. So just as an example, we define various events of interest, coverage points, and a sort of typical approach is to do a cross product. So you might have some interesting set of events, like here we've got a misaligned address, an unknown address, a page miss, so this would be some sort of memory controller logic. We want to make sure these events are happening with different scenarios of the memory access. I'll just wrap up this slide. So here we're looking at, I've labeled this load to use latency, right? So we're requesting a load from memory, for example, and a load to use would be the load instruction itself, which returns data, and then the instruction after it that consumes that register. So a load to use latency of 1 might be a load instruction followed immediately by an instruction that consumes that data from the load. Latency of 2 or 3 would be instructions after that. So, maybe we want to detect all these sort of exception conditions that relate to memory with different load to use latency. We create this coverage matrix. Then we run simulations and collect the coverage data, which might look something like this. So very often we have this unknown address with a load to use latency of 1, but we never do a misaligned address with that latency. And that guides our test development. So we can try to tune either the focus test or the random, the knobs on the random test generation, etc., to make sure we're getting good coverage across the board. Okay, so the test plan would just be full of these coverage matrices. You can imagine a 3D matrix. I don't know, maybe it's the limitation of human thought. We tend to do these two-dimensional matrices. And you can do one-dimensional matrices, of course, as well, just to make sure you're getting these individual events. So I think with that, we'll take a break.